Fine, it's not on yet. So I'm going to give you 5 questions as well, okay? I'll tell you 5 words. So our next speaker is Ruiqi to talk to you about dynamics and accretion variability of misaligned circumbinary disks.
Good morning, everyone. My name is Ruiqi Yang from Macquarie University in China, supervised by Professor Shangfei Liu. Firstly, I want to thank organizers for giving me this opportunity to present my recent work here. And this is also the first time attending the international workshop outside China. I'm really grateful for the hospitality, and the campus is beautiful and the scenery is wonderful. Okay, let's get started. Today's topic is dynamics and accretion variability of misaligned circumbinary disks around eccentric binaries. This work is in collaboration with Jeremy Smallwood, Hongping Deng, Yaping Li, Alessia Franchini, Robin Dong, and Shangfei Liu. So what is a circumbinary disk, or CBD? Generally, there's an accretion disk outside the binary. Due to the binary potential, there are spiral density waves excited in the disk, and the binary could also carve out a low density cavity. But there are some accretion streams that could still penetrate the cavity and sneak into the binary region, forming the circumstellar disk, or says the mini disk. Observationally, from small scale such as protoplanetary disks to larger scale such as massive black hole binaries, circumbinary disks exist. And by early chaotic accretion or other mechanisms, the circumbinary disk could be misaligned with the binary orbital plane. And the numerical studies of binary or multiple systems show that the misalignment is common. And observationally, we already know several systems that are misaligned, such as LS43, the left figure. The disk is misaligned by about 60 degrees, and the right figure is HD98800. The disk is misaligned by about 90 degrees. So this naturally leads to our motivation of the work. How does such misaligned circumbinary disk evolve, and how does the misalignment affect the binary accretion variability? Can the accretion variability serve as a diagnostic for the binary disk misalignment? To solve these questions, we leverage Phantom to run simulations, heavy simulations. We model a 0.5 eccentricity binary. The mass ratio ranges from 0.11 to 1. The disk mass is 10 to the power of -3 binary mass, and the initial tilt ranges from 0 to 180 degrees. The H over R is set to 0.1 at the inner radius of the disk, and we use alpha viscosity parameter 0.01 for long-term simulations and 0.1 for short-term simulations. And we use a locally isothermal equation of state. Let's see the main results. Firstly, the disk alignment. This figure shows the evolution of density-weighted tilt. Different colored curves denotes different initial binary disk tilt. We can see that the tilt undergoes oscillation and is gradually dampens due to the viscous dissipation in the disk. If we focus on the disks with tilt below 45 degrees, they actually will evolve towards coplanar prograde alignment, which means the disk angular momentum vector is precessing about the binary angular momentum vector. And for disks with tilts higher than 45 degrees, lower than 135 degrees, the disk angular momentum is actually precessing about the binary eccentricity vector rather than the binary angular momentum vector. So these disks will evolving towards polar alignment. And for disks with tilts higher than 135 degrees, they will evolve towards coplanar retrograde alignment, which means the disk angular momentum vector is precessing about the opposite direction of the binary angular momentum vector. So generally, there are 3 stable alignments for misaligned circumbinary disk around the eccentric binary, which is consistent with previous analytical predictions by Martin and Lubo. Okay, next result is about the accretion variability. Firstly, the long term. So this figure shows the accretion rate of primary and secondary stars, and also the evolution of inner circumbinary disk of the eccentricity. So the red and blue curve denotes the primary and secondary stars accretion rate using the left y-axis, and the purple curve below is the eccentricity of the inner circumbinary disk using the right y-axis. We notice that there's an alternating preferential accretion phenomenon in such coplanar prograde case, and that's actually due to the disk saddle precession, which means the cavity is eccentric and periodically closer to one star, we increase that star's accretion rate, and this is well studied in 2D simulations. And if we focus on the moderately misaligned disks, such as 45 degrees left one and the 135 degrees the right figure, we notice that there's also alternating preferential accretion when the disk cavity's eccentricity goes really high, and at that time the disk is undergoing strongly warping and even breaking. So to understand this process, I want to show the movie. So the upper and bottom rows are for 45 and 135 degree cases respectively. So with evolution, we see that the disk is precessing, and the disks firstly break in 45 degree case and forming a inner polar disk. This disk is really eccentric, and the break will propagate outward. But with evolution, the inner polar disk gradually circularizes. 135 case breaks later, but the morphology is actually similar to 45 degree case. Okay, so I'll take 3 snapshots to show the evolution. If we focus on the second column, the XZ plane, you can see that the disk is actually undergoing a northerly precession about the binary eccentricity vector, just like the illustration shown on the right side. And if we focus on the third column, we can see that so this is the face-on information of the inner polar disk is actually also undergoing the epsilon precession. So with the combination of both effects, we also see the alternating preferential accretion in polar disks. All right. We also studied the preferential accretion ratio, beta, in the simulations, which is the time averaged value of the secondary star's accretion rate over the total binary accretion rate. And so if this eta is higher than 0.5, then it means the secondary star will dominate accretion, and if it's lower than 0.5, then it means the primary will dominate accretion. So we found that this eta is a non-monotonic function of binary mass ratio. For nearly coplanar prograde disks, the eta increases with decreasing mass ratio. And for disks with tilts higher than 30 degrees, lower than 135 degrees, the eta decreases with decreasing mass ratio. And for nearly coplanar retrograde disks, these disks tend to favor accretion onto the primary star. Now let's see the short-term variability. So basically, we simulated 3 representative cases with initial tilts 60, 90, and 120. And the x-axis is the orbital plane in one orbit. The vertical red dotted line denotes the periastron passage, and the y-axis is the accretion rate. Red, blue, and black curves denotes the primary, secondary, and total binary accretion rate. And we notice that there's a feature which is the double pulses. We can see there's a dominant pulse of the accretion rate, and there's a kink or shoulder structure beside the dominant pulse, and also a minor accretion pulse. And if we plot these 3 pulses phase into the left figure, and we can see that when the tilt is increasing, the dominant pulse phase is actually shifting from periastron to post-periastron, which is really interesting. To better understand the mechanism dynamics behind it, I also plot the movies. So the left figure is the 3D projected figure of the different systems, and the red and blue particles are representing the gas particles that are created before periastron and after periastron, respectively. And pink and green scaters are the binary stars, and the red figure is the accretion rate over the binary orbital plane. So let's see the 60 case. Okay. So if we look at the snapshot, so before periastron, the particles that are created have already bounded to each individual star, and with evolution to the phase at about minus 0.1 PB, the two circumstellar disks will interact strongly and become eccentric. And also you can see there's a bridge structure between two circumstellar disks, and and also the accretion rate increases. After periastron, at around 0.15 PB phase, the two circumstellar disks also interact and become eccentric, but the number of the particles created after periastron is smaller than the particles created before periastron. So this case, it shows the pre-periastron dominant accretion. And this is the 90-degree case. So, okay. Compared with 60-degree case, the particles are not that concentrated around each star, but there are some particles playing out of the circumbinary disk plane, and then finally fall back onto the binary region, and they are more spread out. And also the interactions between two circumstellar disks is weaker than 60-degree case. Since the gas particles accreted after periastron is larger than pre-periastron, it shows the post-periastron dominant accretion. And finally, the 120 case. Okay. So instead, so there's another gas feed channel instead of the circumstellar disk feeding channel. You can see that there are also many gas particles inside the cavity region rather than bounded with individual stars. And the particles are mainly blue particles, which means they are almost created after periastron. So in this case, it shows the post-periastron dominant pulse. So a short summary, for 60-degree case is mainly due to circumstellar disk mediated capture and transit circumstellar disk interaction. And for 90-degree case, we see out of plane and fallback process, and it shows weaker circumstellar disk interactions. For 120 case, not only shows the CSD mediated capture, but also we can see many particles inside the inner circumbinary disk, and it shows a strongly post-periastron dominant accretion. Finally, the implications. So first, the implication is for circumbinary planet formation. This figure shows the circumbinary disk mass at the end of the simulations. And if we focus on the disk around the 45 degree and 150 degrees, you can see they undergo quick depletion of the disk mass. So it might affect the circumbinary planet formation. If you imagine there's let's say a gas planet formed inside the disk, and the disk mass is quickly depleted, then this planet could be decoupled from the disk and becomes misaligned circumbinary planet. In contrast, if we look at the disks near coplanar alignment or polar alignment, they show they can retain more disk mass than the previous disks. So they may provide a stable environment for planet formation. And that may be a reason why, the systems like 99 Hercules could still process polar debris disk when with so long age, like 6 to 10 gigayears. Another implication is for observation. So with more and more such Circumbinary disk system being observed, we will have more like accretion data, like the red figure shows. We can fold them into one orbital phase and to see the dominant pulse relation with the orbital phase. Then we can use our short-term accretion variability results to help like constrain the misalignment of these systems. And also, the misalignment can affect the morphology of the circumbinary disk with increasing misalignment. The cavity size is shrinking. So we hope that we might in the future like combine the cavity size and short-term accretion variability to help constrain the system's misalignment, and we might use MC-FOSS to generate synthetic image or light curves to do that. Yeah. I'll leave the summaries here and happy to take questions. Thank you very much.
Questions? Antoine?
Yeah, thank you very much. This is amazing work that you are presenting here. I have a bunch of questions, so I will only ask one, which is, I'm a bit confused by your final disk misalignment. You have shown 3 regimes, right? One coplanar, one polar, and one retrograde, sorry. But you have something that seems to be in the middle, right? Around like 30 degrees and something around like 140, which seems to stabilize. And so to me, this is very puzzling. Can you explain what's happening in these simulations?
So in this setup, the timescale of alignment for coplanar is really long. So we only simulate 5,000 orbits. Polar disks will align quickly, but yeah, this setup, we cannot see the coplanar alignment achieved within such 5,000 orbits. So if you elongate the simulation, then these disks like around the 150 or 30-degree case, they will finally evolve towards coplanar.
So you think that they will go to a coplanar or polar case, they will not stay misaligned like this?
Yeah, but within the simulation time, we cannot see them go to 180 degree or 0 degrees. But both theoretically and if you change the eccentricity, it will also change the time scale of these disks. Yeah.
Thanks.
Thank you.
Other questions?
You know over what timescale roughly it would reach coplanarity? Like how many binary periods of time you expect those to get to?
Yeah, it's depending like on the alpha parameter and also H over R, and also the binary orbital frequency. You can estimate that there's an equation, but I don't know how to describe that. Yeah, but indeed there are equations to calculate time scale.
I have a follow-on question from Antoine. So you were showing yesterday that planet formation in binaries is probably harder because of the growth of the dust and everything like that. But you were mentioning here that if you formed a planet in these systems, maybe it becomes decoupled and misaligned and all that kind of thing. But following Antoine's work, do you think that actually you are forming planets in these systems?
Yeah, I mean, I think it's still possible. Like, but in our simulations, there's no gravitational instability or some other instability. But if it can figure that, then it might help form like such planets, and then we can see misaligned planets. Yeah, I think yesterday's talk. Yeah, the planets, Circumbinary planets could be formed like in the outside region and might migrate into the inner part. Yeah, because near the cavity, it could be hard to form.
Any further questions? Yeah, go on. You're stopping us from coffee, but go.
Have you looked at how the inclination of the disk affects the binary of the orbit of the binary itself?
Yeah, it's also an important question in this problem. So here we use a quite low mass disk, circumbinary disk, so it's nearly not changing the binary orbit. But if you increase the disk mass, then yeah, it will affect the binary separation and also eccentricity. Yeah. Okay.
Let's thank Ruiqi and our other speakers from the session. Half time. Ali?
Oh yeah.